guarantee that we leave some time for discussion before the session ends. Okay? So it's going to be good, I think. And we make it good. Thank you.
Thank you. I really want to thank Tulio and Jorge and everyone else who involved in inviting me. It's been a long time since I've been hooked up with the Ada community, and it's still one of my big loves. When I write software of my own for personal purposes, like simulating multi-core processor scheduling, I write it in Ada, but it's hard to persuade other people to do that these days around my university. I managed to still force a few students to learn it in my programming languages class over their objections. I'm hoping maybe at this meeting I'll get some better arguments I can give them for why they should be, what Ada is being used for. Okay, I was asked to speak about multi-core scheduling, and it came at a strange time in my life. I've spent a lot of time looking at multi-processor scheduling before multi-cores became popular and cheap. And I thought that multi-core scheduling was simply the same thing as multi-processor scheduling. But as you'll hear in the talk, I think things have changed quite a bit. It's a different story. And to some extent, you hit me at a time when I'm somewhat disillusioned about the subject. So for those of you who are keen on multi-processor scheduling and think you have solutions to all the problems, you'll have a chance to argue with me later and convince me that you really have a solution. Make me feel better, okay? But to me, I think this little simple thing over here on the left looks a lot more like that thing up there on the right, okay? I think the multiple cores are very threatening. Here's the short version of the talk. I think multi-core processors mean more complexity, more choices, more variability, and more uncertainty, and less safe generalizations you can make, and less reliability. That's the short version of the talk. What I'm going to go through in this talk, though, is an attempt to cover these areas. I'm going to talk about some of the scheduling theory foundation and results. I can't do much. For those of you who already know this, it'll seem like nothing. For those of you who don't know much of it, maybe I'll fill in a little bit of a taste of what's been done. But clearly, if this were a talk at RTSS and I were talking about multi-core scheduling or multiprocessor scheduling, I would focus on one area and take 30 minutes just to give an overview of that, just one problem and one solution. And in fact, the amount of work that's been done in this area is pretty astounding over the last few years. Every time I go to an RTSS, RTAS, or ECRTS meeting, there's at least 2 sessions of nothing but multi-core scheduling papers. And there are other meetings besides like that RTCSA and so forth. I'm going to talk about I'm going to try to give an intuitive idea of what multiple processors do to the single processor theory, what the major differences are at an intuitive level with a few examples. And then I'm going to look critically at whether the theory fits the reality of multi-core processors. And I'm going to try to tell you why I think there's a disaster brewing out there, and a few modest plans for survival, but there's nothing very magical about it. Okay, so first of all, why do we have multi-core processors today? You probably know, and I've went into a little bit more depth in this in the paper. This is something that was forced on us by the chip manufacturers who have run out of options. They can't speed up the chips any faster without running into heat problems. And so they decided to take advantage of their ability to squeeze things tighter into the array by putting more cores on the machine, whether we want them or not. They're there, so we have to find a way to use them. The positive side, it means we have more processors to play with, and that means we have more processing power when we need it. And in fact, we can have fewer preemptions because we have multiple processors running in parallel. And we can switch off the unused cores to save power, which may be easier than, say, like voltage scaling. The problems are nobody knows how to write good scalable parallel programs. The supercomputer guys, high-performance computing guys have been beating their heads against this for decades. And it's a big, complicated field. It's very hard. And suddenly, everybody who's doing every other kind of computing is now pushed into that domain. It's a new set of problems for us. Everything's more complicated. OK, so the scheduling theory for multiprocessor scheduling is basically the same as other real-time scheduling theory. It consists of workload models and processor models. The workload models we use are mostly made of jobs and tasks. There's a lot of varieties, but that's sort of the dominant model for real time. And for review here, a job is just the equivalent of a procedure that you execute. It has a beginning, it has an end, it has a finite execution time. And we assume that we know the maximum execution time, and we often call it the worst case execution time. But it isn't necessarily the worst case execution time, it's the maximum execution time. And the maximum is not always the worst case, as I'll try to point out here in a minute. We also have a release time for each job and a deadline, and maybe other attributes for the job. Okay, so terminology in that model, we have an arrival time, earliest possible execution time for a job. We have the time it actually starts to execute, then executes for some intervals, perhaps preempted, perhaps suspended, and then a deadline comes. And if it doesn't complete by the deadline, then we have a missed deadline. So there's a completion time that may be later than the deadline. We have some lateness. This window here from the earliest possible execution time allowed to the deadline is usually called the scheduling window, okay, for that job. The job of the schedule is to map the jobs to processors over time. And a schedule is feasible if all of our constraints are satisfied. In particular, we don't release earlier than the schedule allows, and we don't have any deadline completions that are later than deadlines. Whoops, what did I do here? And scheduling algorithms find schedules for jobs. And we have different kinds of scheduling algorithms. There are various classifications of them, typically static versus dynamic. Usually static are determined offline, and usually dynamic determined online. We have a number of important properties. One of these is what I believe Alan Burns and Sanjoy Brewer coined sustainability, and here I broke it into two words. And so I'm saying an algorithm for scheduling, to be reliable, it has to sustain the ability to find feasible schedules under expected variations for the particular scheduling model. And in particular, job parameter changes that are improvements. And examples of improvements would be shorter execution times and longer relative deadlines. So these are things that intuitively should make the job easier to do, the scheduling job easier to do. This is related to sometimes called sensitivity analysis, where we just look at variations in the parameters over some window. But sustainability has to do with allowing arbitrarily large variations in the direction we consider intuitively to be safe. This is not always the case, though. So for preemptive scheduling, one of the well-known facts is that shorter execution times can mean later completion times. And this is a well-known example, just to help you, to make it precise, though, I'll put it here. So we could have a set of jobs 1, 2, and 3, and in that priority order, so job 1 is highest priority. And if jobs 1 and 3 arrive together and job 2 arrives in time, it gets to start right after job 1 and then job 3, and everything comes out nicely. But if job 1 finishes early, before job 2 arrives, then job 3 starts, and of course it can't be preempted, so it gets to run before job 2, and so job 2's completion time is delayed and it may miss a deadline. So the other element of the basic model is tasks. So a task is a sequence of jobs, usually an unbounded sequence or a series of finite sequences, each which taken in aggregate are without bound. We generally require the jobs in a task to be executed sequentially, and this is where scheduling theory tasks and ADA tasks have something in common. And we have constraints on the characteristics of the job, such as the arrivals may be periodic or sporadic. And the purpose of these constraints is to enable us to do analysis of schedulability. To constrain the workload sufficiently, we can guarantee that it can be scheduled. There are various models. The one that I've spent the most time working on is a sporadic task model, where we have what's called a period, but it really is a lower bound on the separation between arrivals of jobs. We have an execution time, which we call worst case execution time. It's the maximum execution time. And we have a deadline, which is relative to the release time. So this is a generalization of a periodic task. An important metric I'm going to mention later on here is the density of a task. That's the compute time divided by the minimum of the period and the deadline. It's a generalization of the utilization, which is just the compute time over the period. Okay, so a schedulability test serves the purpose of telling whether a given algorithm will find feasible schedules for all the job sequences that can be generated by a given set of tasks. We have exact schedulability tests that say yes or no and mean it. And we have sufficient schedulability tests that say yes and mean it, but no is non-committal. This is like decidability versus semi-decidability, or recursiveness versus recursive enumerability. Okay, so this conference is about reliable systems. Okay, so for a reliable real-time system, we want to have a scheduling algorithm with a test, and the test has to be reliable. So we don't care how good the scheduling algorithm is unless we have a test that works with it that's equally reliable. And if someone tells us, trust me, the system is schedulable, I've tested it, and this is a great scheduling algorithm, it always works, we don't care unless they have a proof and an analytic method that they can show the system is schedulable and always will meet deadlines. When the reality is, for most of these scheduling algorithms and multiprocessors, the schedulability tests are weak. They're sufficient, but not exact. And so they're very conservative, and they tend to give you results that fall short of the reality. That's something we have to live with if we're worried about reliability. Okay, the basic model that most of the research has been done on in multiprocessor scheduling is this little simple, I might say simplistic model, where we have a bunch of processors and a shared memory. And all the processors have equal access to the memory and hopefully are interleaved in some way so that they can get a fair share of the memory between all the processors. And hopefully, what one processor is doing will not interfere with another processor is doing. We're already getting on a thin ice here, though. In fact, that's the way things were, though, when I first got interested in multiprocessor scheduling. I don't remember which of you, I think one of you at least, maybe Tucker, was on the committee that went to look at the Patriot missile system some years ago, where they had a multiprocessor system, and their memory was interleaved, and every processor took its turn on the memory, and that's exactly when it got to access the memory, and it didn't matter what other processors were doing, because they got no more or less than their slot at the memory. And the caches were virtually non-existent in those days, so you could pretty much count on a constant rate of progress for each of these processors running in parallel. And the fact that they were sharing a memory meant that we could move a job from one processor to another more or less without pain. The model is still pretty much the same that people are using for analysis. So all the processors are assumed to have the same speed, or that Sanjoy has done a lot of work on this uniform model where the processors run at different speeds, but they're all linearly related. There's a constant factor different for each processor. But the assumption is that any processor can execute any tasks. And so that's the model. Now, so what makes it different if you have many processors versus one? So I put this picture up, okay? I stole it off the web like these other pictures. So here's one happy, smiling face. It's very easy to deal with one person at a time. Or if that's your wife, it's not my wife, but if that were your wife or your girlfriend, not a problem, right? Okay. Now we get a few happy, smiling faces, and they're not too hard to deal with all at once. That's your office party or whatever it is there. We get a whole lot of them, and then we get something like this, more like the mob. You know, and this is pretty much the way things work as you add more cores. Now, I'm going to run through about more differences. That was sort of a top-level view. But some of these differences are covered by the model that I showed you. They're just differences between one processor and many processors, and you can already see them with that simplistic sort of a model that we put up there. Others of these differences will not show up in the model, and that's why I say I'm pessimistic and I see disasters brewing, because the models that people are using are necessarily simple to permit analysis. But the real life is not that simple by any means.